Hello everyone, I'm Kuma. Have you ever wondered whether it's possible to solve fate battles with our computer? This has been in my mind for a very long time. I've decided to try this by myself, and I will be showing you how I'm doing it in this video. First, how complex is a battle in Fire Emblem Heroes? There are different kinds of measurements for game complexity. Let's start with the state space complexity. The state space complexity of a game is the number of legal game positions reachable from the initial position of the game. It's not easy to know the exact number, but we can get a rough estimate. Here, we have the Inferno Map of Barnhill Battle, Titania and Mist. Let's assume we are playing this map with this fixed team with fixed skills and seals. There are 27 regular tiles, 10 forward tiles, and 9 firing tiles. And there are 3 cavalry units, 4 infantry units, and 3 firing units. So we can get an upper bound of different possible positions with this formula. And then it's possible for each unit to be either dead or alive with different numbers in HP. I'm going to take a conservative estimation here, assuming that on average each unit can be in 3 states. That is dead, full health, or in between. Each unit can also have buff. This can be a buff from skills like ground orders or horn, or a mixture of all this. I will go conservative again and assume it's 2 states for each unit. And the same applies for debuff. Lastly, a unit can be available or it has already acted. It's important to know that the enemy AI in Fate is deterministic. Therefore, enemy phase is just a process between states but not a different state itself. It means we should only consider player-controlled units this time. So, this is a rough estimate of 10 to the power 27 for the state space complexity. And remember that this number can go even higher if we are talking about maps with reinforcements, or if the units, skills, and seals we use can change as well. Next, we want to know the game tree size. A game tree is a directed graph where the nodes are states and the edges are actions. The game tree size is the total number of possible games that can be played. That is the number of leaf nodes or terminal nodes of the game tree. Again, we are going to estimate it, but this time with some actual statistics. All the data here are taken on the Inferno Map of the corresponding hero battles with a fixed free-to-play team. Data on turn 2 and onwards are taken by using moves from a known solution on the turns before. The numbers in white are the valid moves for each turn in the corresponding maps, and the numbers below them are the number of valid moves which all the player units survives after the enemy phase. After removing the top 3 and bottom 3, we take an average for the valid moves and the survival moves. Using this, we can get an estimate of the game tree size for different numbers of turns. We have to multiply it by 24 if we allow swap phases. So for maps which usually end on turn 4, the game tree size is about 10 to the power 20. And it grows exponentially with respect to the number of turns. For each extra turn, the game tree size would be increased by a factor of over 10,000. Also, just like the state space complexity, this would go up if we consider different team combinations and seals. It means that even though it may not be as complex as games like chess or Go, it's still impossible to do a full search on the game tree or state space for fate battles. Before I can get to work on the actual AI, I have to recreate the whole battle simulation such that it is accessible for our AI to be made. To do that, we need to know every single detail of the enemy AI. That include lots of moving parts normal players do not know or do not need to know. For example, will an enemy unit use its assist instead of attack? Why does an enemy unit use reposition instead of moving up? Or why does an enemy unit move in one direction but not the other direction? This is also one of the most popular comments I've received for my free-to-play solutions. Luckily, someone has studied that before. let me give a special thanks to Mia's AI Manipulation Instructional Academy here, which has recorded a lot of minor details of the enemy AI in Fate. However, the logic written there is only 80% correct. Still, that gives me a very good start for my battle simulator. Before we move on to the details, I think it's time to show you a quick demo on the current version of the AI. By the way, don't forget to subscribe to the channel and smash the bell icon to turn on notifications. Your support is very important to me. We are going to play on the Inferno Map of Mythic Hero Battle Service using the theme on the left. I'm using a generic indoor map to visualize the battles. The log may be different, but the terrains are exactly the same. The AI is actually simulating much more battles in the background, while it's showing the battle with the best results in the recent simulations. You can find the statistics of the AI on the upper part of the screen. They are updated together with the battle on display once the previous one ends. Attempts is the number of battles simulated. Nodes is the number of nodes in our tree, and that is related to memory usage. We will talk about this when we go through the details. Elapsed is the time used. Kills, death, and score are about the current battle on display. Best is the best score we have ever had for the whole simulation. On the right side, it shows the steps of the current battle for both player control units and enemy units. Actually, it took me more time in writing this battle simulator than the AI itself. I'm not going into the details of that in this video. If you are interested, comment below to let me know. Maybe I can make a separate video if lots of you are interested. In order to explore the game tree to find the solution without a full search, I'm using my own variation of MCTS. MCTS stands for Monte Carlo tree search. It's a game tree search algorithm. The famous AlphaGo and AlphaGo Zero use their own variation of MCTS combining with machine learning in their AI. There are 4 steps in MCTS: select, expand, payout, and backpropagation. On select, starting from the root node, we select a child until we reach a leaf node. If it's the first time we visit this leaf node, perform the payout for it. Otherwise, we expand it. For each of the valid moves from the current node, create a corresponding child node and select one of the child nodes randomly to pay out. For the payout, starting from the stage of the chosen node, perform random moves until the game ends. We get a score of 1 for a win and 0 if we lose. We backpropagate the result to the parents until we reach the root node, such that each node can update its own record on the total number of wins and tries for itself and its child nodes. So how exactly do we select a child? MCTS is usually used together with UCB1. It converts the average score into decision values. If at least one of the child nodes is never visited, we select one of these randomly. Otherwise, we apply the following formula for each child and select the one with the highest value. Small n is the number of tries of the child node. The capital N is the number of tries for the current node, while x is the number of wins of the child node, and c is the exploration constant, which is root 2 by default. The first term of the formula is the average number of wins of the child node. It corresponds to exploitation of deep variance after moves with high average win rate. And the second term corresponds to exploration of moves with fewer simulations. The formula tries to balance the exploitation and exploration of the game tree in order to gain a good result without running a full search. because we are solving a puzzle instead of playing 1 versus 1 game. If we keep using the score of 1 for success and 0 for failure, then obviously it will be totally pointless. It will be all 0 until we find a solution. And before that, UCB1 cannot help us with exploitation. We have to set our own score. Here is the formula for the version 1 of our AI. We have 3 criteria for scoring. Enemies defeated. This is very straightforward. I believe no explanation is needed. And then we have players' units alive. I have implemented the simulation a little bit different from the actual game. If it's in the enemy phase, the battle would not end immediately when a player unit is defeated. Instead, it ends after the whole enemy phase. I believe this can help to identify bad moves that may lead to multiple defeats in enemy phase. The last one is about phase remaining. I've set a phase limit, the default is 20. This is used to suggest the AI to choose a solution with fewer moves. I knew that this may cause a problem making the AI fail in finding any solution. But for our first version, let's just try and see. It didn't take too much time for me to implement the first version of our AI. I used the Inferno Map of Downhill Battle, Titania and Mist for testing, because it was available at that time. The score on display is multiplied by 1000. You can see that we are able to simulate around 300 battles in 1 second. This is not too bad, but I know we can do better. Also, when the program is run for a long time, the memory goes up very quickly. This is expected, because we have to store the tree of MCTS. But we can optimize this a little bit. So let's head back and optimize it first. For memory, we can remove nodes which are no longer in use. These are nodes where the game ends and it cascades to the parent nodes when all the child nodes are removed. Also, whenever we are getting over 600,000 nodes for our tree, we are going to confirm one move and discard all the sibling branches. For performance, first we have to make use of the multi-core CPU by using multi-threading. There are multiple ways of doing it. The easiest way is called root parallelism, creating a separate root for each thread and one MCTS from there, so each thread has its own tree. This is the easiest because no memory is shared between threads, so only minimal changes are needed in the code. However, for the same reason, efforts could be wasted for testing the same nodes on different threads. So instead, I went for the next method, tree parallelism, where a single tree is being used for all threads. For this method, some kind of synchronization is required between threads, and a little bit more coding is needed. Another performance upgrade is by caching. The enemy phase is taking the most time in the simulation, and one of the heaviest operations is various path findings, which could depend on movement type, terrains, obstacles, etc. By caching these path finding results, we are able to speed things up a lot. With all these optimizations, let's try the map again. Now we are able to reach about 4000 simulations per second. I'm using a 6-core CPU with 4 cores aside for the AI. And we are showing log count as well. It's the number of logs we have in the MCTS. For performance reasons, each log stores its own game board. And that is the largest portion of memory used by the AI. I'm going to speed up the playback from here. It took 4 minutes for the AI to figure out this solution. You may have noticed that the AI is not very smart. There are several moments it has almost made it, but seems it didn't learn from that experience. Let's be clear that this version is different from the one in the demo earlier. Now let's give it another test with the Inferno Map of Mythic Hero Battle Surface. The AI is still repeating the same mistakes. I call them the same mistakes, but it is important to note that they are actually different paths. The AI is programmed to not repeat the same moves. It may look similar to our human eyes, but there are minor differences. For example, in one path, Ike moves first before air, and in another path is the reverse. And if you remember, this is about the state space we mentioned. In this AI, we do not take that into account. This could be part of the problem where the AI is not performing well, but there is much more than that. After spending more time to think as well as reading more papers, I have a better understanding of MCTS and UCB1. UCB1 was designed to solve the problem of multi-armed banding, which assumes each arm returns a reward following a probability distribution. Looking at the UCB1 function, we can see that only the average score and the number of tries are taken into account. Variance or standard deviation is not considered. So for our case, as I am using a reward of real numbers between 0 to 1, this could create a problem if the actual reward has a much smaller variance than expected by UCB1. For example, if the actual score is always between 0.1 to 0.2, the difference of the first term would be so much smaller, making the system to favor exploration over exploitation. Also, MCTS does not work very well for extreme situations. This is because MCTS maximizes expected win probability but not the score margin. The computer Go community uses a method of dynamic komi to work around this. Komi is Go term for a pawn penalty imposed on one of the players. This method tries to make the game more even by using an internal komi determined based on the current board situation. This does not apply to our case directly because we are already using a score instead of win count. However, the dynamic nature could be something we can use. Some papers also mentioned guide payout, instead of payout using completely random moves. We choose moves which are known to perform better with our domain knowledge. These papers suggest that this would make the AI smarter. So with all this knowledge, we are going to upgrade our AI. First, we are implementing the guided payout on this new version, prioritizing dance and attacks over other moves. Also, we are modifying the UCB1 selection like this. Instead of forcing our score to fall between 0 to 1, we use unbounded score. Before putting a score into the UCB1 function, we normalize our score, dividing it by the best score minus the FH score of the parent node. And the new score contains 5 components now: enemies defeated, enemies HP missing, player units alive, player unit HP remaining, and phase left. This video is already 20 minutes long. I'm going to finish the video showing our AI version 2 playing on Sophie's Inferno Map. However, this is not the end of our AI journey. There are more upgrades that have been done or to be done. I have also skipped several details to keep the video from being too long. If you want to know all this, remember to like the video and share it to your friends. Then maybe I can create part 2 of this. Without further ado, let's get into the battle. This time we allow swap spaces. If you have watched my latest V2Page solution on the Inferno Map of Mythic Hero Battle Surface, you may realize that it looks familiar. And yes, it is the first AI-assisted solution, and also the only one I've uploaded at the moment of making this video. So thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up and subscribe to the channel. Also, remember to click on the bell icon to receive notifications on my new videos. You can also find the links for my cheater and Discord down below. Hope to see you guys next time.